Okay, Assalamualaikum warahmatullahi wabarakatuh. So now we look at the new topic, our topic 3, based on specific energy and control section, part A. Okay, in this topic, so at the end of this chapter, students should be able to apply specific energy concept, okay, in determine the critical flow condition, okay, analyze flow over broad criteria, and analyze flow through with constriction. So this is the three subtopic that you must know, okay, after we learn in topic 1, chapter 1 and chapter 2. Okay, now we look at the concept of specific energy. Okay, so a specific energy is the energy of flow measured by respect to the channel bottom. So the energy of flow measured with respect to the channel bottom. Okay, so in case in your test or in your final ask you to explain what is the specific energy, you can explain based on the energy of flow measured with respect to the channel bottom, and you just put this formula. Okay, so the E is the specific energy formula is equal to Y plus V2 squared over 2G here. Okay, so this is the energy grade line here. So energy line slope here as F. Okay, and this is water surface of hydraulic grade line SW, and the bottom slope S0. So we have the three part of this one, energy line, hydraulic grade line, and bottom slope here. Okay, with the Z1, Z2, Y1 and the Y2. So with the height, okay, the distance of Z1 and the Z2, Y1 and Y2. Okay, and also the specific head here, okay, specific energy here with the velocity 1 and velocity 2. Okay, so now we look at the concept of specific energy is useful in defining critical depth, okay, to get the critical depth, and in the analysis of flow problem. Okay, so in chapter 2 we have learned the how to find the normal depth. Okay, so why not? Okay, now in topic 3, so we learn the why critical. Okay, why critical is we get as the YC. Okay, critical depth, and we must also find the subcritical, okay, subcritical, critical depth and supercritical. Okay, so this is based on the formula, this formula for specific energy. Okay, energy, specific energy here, E is equal to Y plus Q2 squared over 2GA. Actually this is Q is equal to AV. Okay, so we get to get the, okay, and you find actually it's at the V squared over 2G, so you just put the Q here, okay, until you get the value here. Okay, actually it's also the same, Y plus V2 squared over 2G, okay, based on the previous year. Okay, from the previous year, so you can change based on this formula here, so you can change to here based on this, okay, formula here. Okay, so now we look at the parabolic, okay, graph here. Okay, at the E minimum here, E minimum, so we get the Y critical. Okay, at the Y critical here, this is the E minimum. Okay, at the E1 is equal to E2 here, so we get the Y1, Y subcritical and supercritical depth. Okay, so we get the subcritical when front number is less than 1. Okay, supercritical we get when the front number is more than 1, and the critical is front number is equal to 1. So this is, you must remember these types of Y. Okay, Y critical, Y subcritical, and Y supercritical. Okay, so variation of E with Y is represented by a cubic parabola. Okay, now we look at the alternate depths and critical depths. Okay, for a specific E, okay, except E minimum, there are two flow depths with Y1 and Y2. Okay, So y1, so we get the subcritical for y1 and supercritical is y2. So these two depth we call as alternate depth. Okay, alternate depth. So if there is energy loss, okay, during hydraulic jump, y1 and y2 are known as conjugate, okay, conjugate or sequence depth. Okay, so this is only during hydraulic jump. Okay, so the y1 of supercritical and subcritical is also known as the conjugate depth. Okay, so critical flow occurs when specific energy is minimum with E minimum and the YC is critical depth. So note here, negative flow depth is not possible. Okay, so no negative for flow depth. Okay, so with the specific energy here, okay, E equal to Y plus Q squared over 2GA squared here. Okay, now you just using the dE dy, okay, differentiate based on this formula. So you get the dE over dy here as the 1 minus q squared over ga power of 3 times by dA dy. Okay, so this is using the dE over dy. So at minimum, specific energy E minimum, y is equal to yc and A is equal to AC. So you must remember this one, okay, for y E minimum. So the y is equal to yc and A is equal to A at a critical. Actually, this is area at critical part, okay, at the critical section. So based on dE dy, so to get the minimum E, so you must put here is 0. Okay, so we get the from this formula, so we get here, okay, so 1 minus by q to, okay, q power of 2, okay, divided by this one. Okay, so dA dt actually from this okay, from this cross section here, so we know that actually we have learned that this top width is based on the chapter 1, okay, and the chapter 2. Okay, so d here, t here. Okay, to get the t here, so we must get the dA or dy here. So that's why you get the tc here. Okay, dA dy here, you just change, okay, change the dA dy here, change the dy here to get the t here. Okay, so actually t is equal to dA dy. Okay, so we get, after you just change here, so we get the formula to this formula, and based on the here, KTC, and this one we get the, until you get the this value. Okay, so actually this is the Froude number formula. Okay, so we have learned the Froude number in chapter 1 and sorry, in chapter 2, chapter 1 and chapter 2. So we get the Froude number here is 1, so we get the minimum here, so we get the Froude number is equal 1, is we get the supercritical. Okay, based on this, okay, Froude number is 1, so we get the critical, okay, critical depth. Okay, so with the critical depth, so we get the Froude number 1. Okay, so that's why we see we get Froude number is equal 1. Okay, so the YC is when at the y is equal to yc. Okay, so when this is E minimum. Okay, so E minimum, so we get the condition of critical depth with the Froude number is equal to 1. Okay, so this is specific energy of flow in rectangular section. So we just look at the rectangular section first here. Okay, so in rectangular section, we know that the Q is equal to QB here, or Q, small q is, okay, discharge per unit weight is equal to Q discharge divided by the B. Okay, so you just can conclude here. Okay, based on the specific energy at the previous slide, okay, we can change here the Q is equal to QB here, so we can change the Q squared here and 2GY2 here. Okay, so this is based on the rectangular section. Okay, for other sections, so we can use from the previous formula. Okay, we use also E equal to Y, okay, plus Q squared over 2G Y2. Okay, actually at the previous slide here. Okay, so we get the other section, we can use this one. Okay, A2, sorry, UA2. Okay. Okay, for the other channel section, so you can use this one. Okay, for only the rectangular section, you can use this one because the Q is equal to the discharge per unit weight is equal to Q over B here, or Q here. So we get the, so we just only put for rectangular section. Okay, so rearranging from this formula, so we get the Q small here, discharge per unit weight is equal to this formula. Okay, so this formula only for rectangular section. Okay, so the variation of Q with Y is represented by the flowing curve here. So we get the flowing curve here. Okay, so we get the flowing curve here. Okay, at Q maximum here, so we get the critical flood number and we get the critical depth. And at the Q1 is equal to Q2 here, so we get the Y supercritical and Y subcritical. Okay, we get this formula. Okay, this is only for rectangular section. Okay, for other section, so we just use the previous formula. Okay, so for a specific Q except Q max, there are two flow depths, Y1 and Y2. Okay, so this is called conjugate depth. So this is for the Q max here, okay, using the Q. Okay, using the conjugate depth. Okay, so critical flow occurs when discharge per unit weight is maximum. Okay, so this is maximum. Okay, so in the previous slide, critical flow occurs when E is minimum and we get the Y critical, okay, using the E minimum. So now we're using the discharge per unit weight, okay, with Q maximum. So we get the critical flow occurs. So we use this formula, okay, to rectangular section only. Okay, so keep here until you get, okay, so we use this formula. Okay, no need to worry about this one, so we just only use this equation. Okay, so this equation for rectangular section only, so we get the value here. Okay, so now we look at the state of flow can be established by comparing y naught with yc. Okay, after we learn the y naught in chapter 2, okay, so now we learn the critical depth in chapter 3. So using this characteristic here, okay, flow condition is critical flow when the front number is equal to 1. Okay, y naught is equal to yc. That means that y is equal to yc. Okay, the flow depth is equal to yc, so this is critical flow. Okay, and front number less than 1. Okay, and y naught is more than yc, so this is called subcritical flow. Okay, and front number more than 1, y naught less than yc, so it's called supercritical flow. Okay, now we look at the example activity, also activity 3.1 here. Okay, the rate of flow, okay, the rate of flow in a 3 meter wide rectangular channel is 10 meter cube per second. Okay, so calculate the specific energy if the depth of flow is 3 meter and 1.2 meter. Okay, so the given Q here, okay, the given Q here is 10 meter. Okay, 10 meter cube per second and B is 3 meter here. Okay, so when Y is equal to 3 meter, okay, so this is using the rectangular channel. Okay, so automatically you can use this equation, okay, or you can use the Q equation. Okay, so you can use this equation. Okay, because this is given the Q here. Okay, so maybe you can use to get the Q, the discharge per unit weight here, so you just using the Q is equal to Q over B. Okay, so you can use this equation. Maybe you can use this equation and just put to the formula here. Okay, so and you could and also use this formula y plus q, okay, square over, okay, y, okay, 2gy 2gy squared, okay, like this equation here. Okay, from the rectangular section you can use this equation or you can use this equation first. Okay, so you can use this equation also. Okay, so now, okay, just look at this formula here. So you just put all the value here. Ke, so the q is 3 meter, y is 3 meter, and plus the discharge here, the 10 power of 2, and just put the value of 2 and times by the g and times by the area actually for the rectangular channel here. Okay, okay, they give you the this is b. Okay, they give you the this is b. Okay, and this is the y. Okay, okay, so y you use the 3 meter. Okay, y is using the 3 meter and the y using the 1.2 meter. Okay, so you get the area. Okay, so area of this rectangular channel is by. Okay, that's why you get this formula. Okay, to get from this. Okay, so you get the b is 3 and the y also 3 here, so you get the value here until you get the value of 3.063 meter. Okay, to when the y is 3 meter. Okay, when y is 1.2 meter, so you just put all the value here. Okay, okay, and you get the value of this 3.1.593. Okay, with the when the y is 1.2, this is why when y is 3 meter. So this is the concept that step by step you must calculate, okay, to get the specific energy, because to calculate the specific energy. Okay, so now we look at the calculation of critical depth. Okay, so this is the calculation for critical depth. So in chapter 2, so we have the calculation of normal depth using the try and error. Okay, trial and error graphically and using the design check. Okay, for critical depth, so just only two methods. Okay, the trial and error graphically. Okay, only two methods. Okay, for normal depth, okay, for normal depth we have three methods. Okay, try and error, okay, graphically and design chart. So now the critical depth just only two methods. Okay, so now we look at the critical depth for trial and error. Okay, for all sections, so you must remember this one. So for all sections, so during critical flow with the E minimum, so we use this formula. Okay, for all sections. Okay, so for all sections, so we use this formula from this equation, from this formula, so we rewrite as a function here. So we usually use this formula. Okay, so this is formula to get the critical depth for all section. Okay, for rectangular channel with the T is equal to B and A is equal to BY. Okay, so it becomes 2 from this one. Okay, AC here and Q2 here. So, okay, so from this formula for all section, okay, this is all section. Okay, all section. Okay, so all section here, this is formula for all section. Okay, so from a rectangular channel, so you can put the A based on by here. Okay, so we get the A is b3 here and the y power of 3 here, and the tc is also the b. Okay, t is equal to the b here. Okay, so we get the, this is for rectangular. Okay, so the rectangular section. Okay, so this is rectangular section. Okay, so from this, well, you just convert to this, we get here. Okay, until you get the value of, okay, this value. Okay, from this one, so we know that the Q is equal to the discharge per unit weight is Q over B. So you just change to this equation. Okay. Okay, and we change to the, and to this question. Okay, so this is only applies to rectangular channel. Okay, so this is YC. To get the YC direct, okay, this direct formula here, you get the YC using rectangular channel. Okay, to get the YC for all sections, so you must use this equation. Okay, so you must use this equation to get YC. Okay, for rectangular channel, so you get this to get YC. Okay, so there are two formula based on all sections. So use this equation, you use this formula, and for rectangular channel, you use this formula. Okay, now we look at the critical depth also occurs when Q is maximum. Okay, so when maximum, so from the Q here, okay, based on the previous slide, so we just put the E here. Okay, and you differentiate, okay, differentiate the Q with respect to Y. Okay, so you get the E minimum, so until you get this formula. Okay, so this formula, okay, no need to worry about from this one to this one, from this one or this one, no need. Okay, you just refers to this formula only. Okay, you just refer to this formula only. Okay, so you get the E minimum. So it only applies to rectangular channel. Okay, if for other channel, okay, so you can apply based on this, you can apply based on the previous slide. Okay, because using the Q discharge per unit weight is only for rectangular channel Q here. Okay, so now it is for rectangular channel to get the E minimum. Okay, to get the E minimum for the other section, so you must use this formula. Okay, for other section. Now we look at the critical slope. Okay, critical slope is used to categorize the type of channel slope. Okay, when types of slope is critical slope, when S naught is equal to SC. SC is critical slope. Okay, when my slope, so when the S naught is less than SC. Okay, is steep slope when the S naught more than SC. So this is critical slope SC can be calculated by equating Manning resistance flow equation to critical flow depth. Okay, so based on this equation here, based on all section here, okay, and we know that the critical slope S0 is SC, so you just put the SC here as the, until you get this formula. Okay, so don't worry. Okay, we just use this formula for critical slope. Okay, actually for this critical slope, so we given in your, on this formula will given in your test or in your final. Okay, so this is the critical slope. Okay, for based on Manning resistance here, so you just use the. So now we look at the activity 3.2 here. Okay, a 4-meter wide rectangular channel. This is also use the rectangular channel. Okay, Okay, and we know this is the B, and we know this is Y. B, and this is Y. Okay, so if the discharge in the channel Q is 25 meter cube per second and bending coefficient N is 0.02, find the critical depth, find the critical velocity, and find the critical slope. Okay, step by step. So it's given data here. Okay, the data is Q, the B, and the N. Okay, for Manning. Okay, so because this is rectangular channel, so you just use this formula YC to get the critical depth. Okay, so you just use this formula because this is rectangular channel. So use the YC here, just put the data here, so you get the value of YC 1.585 meter. Okay, to get the velocity critical here, so you must use this. This is the Froude number. Okay, use this is formula for Froude number here. Okay, so use this formula, just put here. And for rectangular section, we know that the D is equal to Y. Okay, so you get the YC here. Okay, YC is the formula, the value that you get from the previous slide, the previous calculation. So you put here. Okay, so you get the velocity critical is 3.943 meter per second. Okay, so now use the critical slope. Okay, the critical slope for only the rectangular channel here. So you just put the formula here and put the value here. Okay, so for rectangular channel section, so we know that the T is equal to B here. Okay, so you just convert the T based on the B. So that's why we get this formula. Okay, because the A we just convert to the Y. C here terus. Okay, just based on the YC here. Okay, so now we look at the put all the value here. So you just put the 0.02 is for the N, and the G is 9.81, and the YC we get 1.585 and put here. Okay, the RC we know that the R is equal to A divided by P. Okay, yes, that's why you must find here for based on the rectangular channel. Okay, so we use the formula in chapter 1, okay, to get the R here. R is equal to AP here. Okay, that's why you must put 2 here. Okay, and we get the value of critical slope is 0.007328. Okay, so now look at the activity 3.3 here. Okay, infinitely wide and straight river has a discharge of 5 meter cube per second per meter. So this is called Q, small Q. Okay, the discharge per unit weight. Okay, the small Q. So this is small q because the discharge per unit weight here, M here. Okay, so calculate critical depth. Okay, calculate the Froude number of the flow when the flow depth is 6 meter and determine the type of flow. Okay, to find the type of flow and find the Froude number. Okay, so and third, to find the critical slope. Okay, critical slope of the channel if Manning coefficient N is 0.0044. Okay, so based on the river characteristic given in A here, okay, so find the possible depth of flow Y2 for the same specific energy and the corresponding Froude number with the same Froude number that we find from the A here. Okay, so the solution here, the Q is 5 meter cube per second per meter and Y is 6 meter. Y flow depth is 6 meter and N is 0.0044. And for infinitely, the very wide, okay, wide, infinitely wide and stretched river, so we can conclude that is the wide channel. So we conclude that R is equal to W. Okay, so this is in wide channel. Okay, now we look at the wide channel is based on the rectangular channel. Okay, so you just use the critical depth formula here. Just put the value and you get the 1.366 meter. Okay, so because the very wide channel, so this means that the very wide rectangular channel. Okay, so that's why we use the YC here. Okay, so for the rectangular section, so D is equal to Y here. So use the Froude number formula. Okay, so you just put the value here until you get the 0.1086. So this is less than 1. So if the Froude number less than 1, so this is types of subcritical flow. Okay, so this is subcritical flow. Okay, with the value of Froude number here. Okay, so for rectangular section, so T is equal to B. So we use the critical formula for slope. Okay, so we put the value here. Okay, and YC, okay, based on the YC here and the R here, because we know that the T is equal to the B. Okay, so just put here 0.0044 power of 2 times by the G 9.81. Okay, and divide by the YC. Okay, 1.366 power of 1 over 3 here. Okay, so you get the value of 0.0001712. So the value of critical slope. Now we look at the B. Okay, so when the specific energy at 1 is 6 meter is the same as calculation in A. So we use the formula here, the formula for specific energy. Okay, so formula for specific energy with the Y1 is 6 meter. So you just put the value here. Okay, so with the Y1 is 6 meters, so we get the value of E1 is 6.035 meter. Okay, you get this value. So using the alternate depth of Y1 is 6 meter, and we know that E2 is equal to E1. Okay, so that's why this is the same. Okay, E2 is the same value of E1. Okay, so you still using this formula for specific energy, but Y1 you change to Y2 because you want to find the Y2. Okay, so using this is called alternate depth. Okay, with the E2 is equal to E1. So we use this specific energy with the Y2. Okay. Okay, so we get the Y2 is Y2 plus Q of power of 2 divided by 2 GY2 squared. You get the value of the same 6.035 here. Okay, and you just calculate and solve this formula until you get the Y2 is 0.4789 meter. So the Y2 here. Okay, we know that the Y1 is 6 meter and the Y2 is 0.4789. So at Y2, okay, 0.4789 meter. Froude number is using the Froude number. Okay, you know that the V here, okay, is equal to QG here, and also use this equation. Okay, with the Y2. Okay, you just put the Y2 here, you get the value of Froude number is 4.817. So this is more than 1. So this is supercritical. So this is for the solution for B. So we get the supercritical flow. Okay, for the activity 3.4 here, so for a trapezoidal channel. So this is trapezoidal channel. Okay, so using the trapezoidal channel, so we use the formula for all section. So this is formula for the all section. So you use here. So this is the data here. Q with the Q is, okay, 17 meter cube per second. B is 6 meter and Z is 2. Okay, Z is 2. So you must find the area. Okay, you must find the area of this trapezoidal. You must find the T here. Okay, the T of this trapezoidal. Okay, so you must refer to the formula for this trapezoidal. You must refer to the chapter 1. Okay, the table that the other all section. Okay, the formula. Okay, so now you just put the here. Okay, to get the YC. So using the try and error method. So this using the try and error method. Okay, so you just put here. Okay, and then until you get the YC is 0.8468. Okay, so to get the YC, okay, based on trapezoidal channel. Okay, if the rectangular channel, you just use the direct equation based on YC. Okay, it's so simple. Okay, but for the other channel, so you must use this OR section. So you must using the try and error section. So you must create the table here that I mentioned at the same as the same in chapter 2. Okay, based on you must know that why not. Okay, this is YC. Okay, and this is the value of here, value of YC here. You just put at this column. Okay, so maybe you just put the YC. Okay, maybe you can set is 1. Okay, so what's value here? Okay, maybe you get the 0.5. Okay, you get the 0.8. Okay, you get the 0.9. So the value, so maybe you get what value you get here. Okay, until at the value here, so you get the 845. Maybe you get the value of 7.365. Okay, based on this value. Okay, that's all you get the value here, put here. Okay, so this is try and error. Okay, for based on try and error, you must do this. You must show this table here. Okay, how you get the calculation, you get the value of YC here based on the value of in this column. So this is column 1. Okay, this is called the column 2. Okay, so the column 2 is based on the value here, and okay, the value here to get the value of this one. Okay, so this is the try and error method until you get the YC is 0.8468. Okay, so using the graphical method, okay, so critical depth of low YC can be solved by plotting A against here. Okay, so this is based on graphical method. So it's plot of A C power of 3 of T, or this one. Okay, so you just highlight of this. Okay, using this formula and also this one. Okay, this is more on graphically method. Okay, so look at the activity 3.4 of 5 here. Okay, so for our trapezoidal channel, so this is using the trapezoidal channel. Okay, with bottom width B is 6 meter and side slope at Z is 2. Find the critical, this using the trapezoidal channel. Okay, find the critical flow depth if the discharge is using the graphically. Okay, so you given data here. Okay, so you must use this all formula section. Okay, for all section, so you must find, okay, the value here until you get the Q power of 2, you get the value of 29.46 here. Okay, so AC over TC here. Okay, and this is YC. AC over TCC, you get this formula. Okay, based on this one. Okay, okay, now you get the YC here, and here AC of TC is this one. So you just put here. Okay, this is graphical method. You must draw the table also based on also the try and error method. You must have this table here. Okay, so and you just put the 2, you get the value of, okay, and when you put the 0.5, you calculate from this calculation. Okay, so you get the value of this one. Okay, when you put 0.7, you get the 15.79. Okay, when you get the 0.8, you get 24.43. Okay, now you must sketch the graph. Okay, you must draw this graph here. So the width, the x-axis is AC power of 3 divided by TC, and the axis YC here. Okay, so the axis here. So you just draw this. Okay, draw this from this table here. So you just draw this line, the blue line here. Okay, so at the one here, okay, at the one, you get the 51.2. Okay, at 51 here, so you get the 1 here. Okay, it's this one. Okay, you get the at the 1 here, you get the 51.2. Okay, so now you look at the at 0.5 here, so you get 5.36. Okay, at 0.6, 0.5, and 0.5 here, you get 5.36 here. Okay, you get the 5.36. Okay, and at the 0.7, at the 0.7 here, okay, this is 0.7, 0.7, this is 0.5. Okay, you get the 5.36 here. Okay, and the 15.79 at the 0.8, at the 0.8, so you get 24.43 here. Okay, you get the 24.3. Okay, now you want use this value here. Okay, 29.46 you get. So you get the 29 point. Okay, so you get, maybe you get this at this first here, 29. Okay, it's 29.46 maybe. Okay, so you get the 29.46. So you get this line. Okay, you get this line here. Okay, and you just put the line here until you get the value of, okay, so you get the value of this 0.84. So maybe you get the 0.84 based on, so you must catch this graph in your graph paper. Okay, with the scale. Okay, so if you draw this graph with the scale, so you can get the scale of the value of 0.84. Okay, so based on, you draw this graph in the scale paper. Okay, the graph paper with the scale. Okay, then you get the value of 0.84. Okay, for graphical method for get the YC, so you must also use the try and error method based on this table, and you must draw the graph. So this is the method. So now we look at the control section. Okay, after we have learned the YC based on the formula that given, okay, for rectangular section and also the all section, the formula. So now we look at the control section. Okay, a control section is where for a given discharge Q, the flow depth Y and velocity are fixed. Okay, so the control section. So the critical depth YC is also a control point, since at this section float number is equal to 1. Effective when subcritical flow change to supercritical flow. So when supercritical flow change to subcritical flow, a hydraulic jumps usually bypass the critical depth as control section. So the control section controls the upstream or downstream flow. So this is the definition of control section. So you can explain based on, if your final or your test asks you to explain briefly on control section, so you can explain based on this theory. Okay, so example of control section here is flow from a mild channel to steep channel. So this is mild channel, the flow from this part here. Okay, flowing from this one, mild channel, to the steep channel here. So we get, this is a control section based on, at this part here is a control section. Okay, from the YC, from the Y naught, the normal depth we find from this flow, and then at the control section we get the critical depth, and then we get the normal depth. Okay, based on the steep slope. Okay, this is normal depth, normal depth based on the my slope. Okay, and after the control section, so we get the normal depth based on the steep slope. Okay, in the steep channel here. Okay, so, and the second here is the my slope channel discharging into a pool. Okay, when is the, from the my slope channel here. Okay, with the normal depth is Y naught. Okay, after the control here, okay, we get the Y critical, so we just enter to the pool here. So this is the example of control section. Okay, so actually for this one, if in your test or in your final, to list and state, or list or state the example of control sections, you can mention based on this figure. Okay, so free flow overflow is sudden drop when it's flow from the horizontal back and have control here and suddenly drop to here. So this is the control. The control is at this part here, we get the YC. So actually for control section, so we must get the critical depth here. Okay, so and reservoir water flows on a steep slope from the reservoir here. So and water flow from this reservoir, we have the control here and we get the YC, and then through to the steep channel we get the normal depth here. Okay, so this is the example of control section. And also with the flow through sluice gate here, with the flow here, with the gate here, sluice gate, and normal depth here with the mild slope here, with the mild slope here, sorry, with the mild steep slope, sorry, mild channel. Okay, based on the my channel here, so we have the control here at the sluice gate and also control here before the sluice gate, so we get the Y critical. Okay, and also we get the Y critical after the hydraulic jump here. Okay, so this is based on the hydraulic jump. So flow over spillway based on the Y naught here until you get the YC here based on the control section at the spillway. Okay, now or we can follow that flow over broad crested weir. Okay, based on the broad crested weir here, there's control here and we get the YC. Okay, and flow through constricted channel with the control YC here. This is constricted plane view. Okay, and we get the control and get the YC here. Okay, so now we look at the flow over broad crested weir. Okay, flow in a prismatic open channel is uniform if there is no obstruction of a hydraulic structure. Okay, if broad crested weir is installed, uniform flow change to non-uniform flow. Okay, change to the water surface profile is influenced by the weir height h and the flow condition before the weir upstream flow, either supercritical or subcritical. Okay, so at this part here, okay, at the zero here, okay, depth the Y normal. Okay, Y naught is normal depth of flow. Okay, after flow is through flow through this weir, and we have the weir here. Okay, so we get the depth of flow just before weir is at 1 here is Y1. Okay, the depth of flow on the weir, the 2 here is Y2. Okay, and this is Y1, this is Y1. Okay, this is Y2. Okay, depth of flow on the weir, and the Y3 is depth of flow just after weir, so we get the Y3. Okay, so this is flow over broad waisted weir, this is broad waisted weir. Okay, so they must have the Y naught before. Okay, they have must the Y1, the Y2 at the on the weir, and Y3 after the weir. Okay, so this is concept in lab. Okay, so this is the using the plate weir here. Okay, so rectangular overshoot weir plate shown here. Okay, so this is also the broad crested weir here with the rectangular streamline weir shown here. Okay, and also the V notch. This is using the V notch. Okay, actually this is in lab. You is using this laboratory test. Okay, based on the plate weir. Okay, with the V notch, and also the dam spillway with weir. So there's also the weir here. Okay, and this is called the hydraulic jump here, and this is based also hydraulic jump occur here, and hydraulic jump is occur here. Okay, and also the hydraulic jump. So this is based on the minimum height of weir H minimum. Okay, height of weir H determines the depth of flow above the weir Y2, whether Y2 is equal to YC or not. Okay, so this is based on the minimum height. Okay, H minimum is minimum height of weir which will start to produce critical flow depth. Okay, above the weir Y2 start to change to YC. Okay, this is based on the minimum height of weir. Okay, so generally depth of flow above the weir Y2 is if H is less than H minimum and we get the Y naught is not equal to YC. Okay, so when H is equal to H minimum, Y2 is equal to YC. Okay, when H is more than H minimum, so Y2 is equal to YC also. So based on this condition here. Okay, so therefore Y2 is equal to YC and E2 is equal to E minimum, E2 is equal to E minimum if H more than H minimum. H more than H minimum or H is equal to H minimum. So based on this condition here, so we get the Y2 is equal to YC and Y2 is equal to E minimum. Okay, based on this concept. Okay, now we look at the condition here. Okay, based on the case 1. Okay, based on the year. So actually this is base case 1. They have the case 1, case 2 and case 3. Actually based from this figure we can learn from this case. Okay, from this figure here. Okay, I explain based on this table. Actually this table based on the previous slide. Okay, so condition of upstream flow when y is the y here. Okay, with the case 1 with the h and y here. Okay, h less than h minimum or e minimum plus h is less than e naught. Okay, e at the normal. Okay, at the normal is a submerged weir. Okay, we get the y1 is equal to y3 is equal to y naught. Okay, so actually this table is given. Okay, no need to worry. Okay, so maybe for the case 1 and case 2, maybe you can understand because they have the h is case 2 h is equal to h minimum. Okay, e minimum plus h is equal to the rarely occur. Okay, so and the case 3 is based on the control weir. Okay, so this is based on the when the subcritical and the supercritical here. Okay, so we get the value here of this control here. Okay, for this y not here and the t here. Okay, so this is based on the from the control here. Okay, so now we look at the step in analysis flow over broad crested wheel. Okay, based on the step by step here. Okay, you set step 1, you must calculate y naught and calculate the yc. Okay, y naught and yc. So you must determine state of upstream flow y naught either subcritical or supercritical by comparing by yc. So you must know that y naught more than yc is subcritical upstream. Okay, y naught less than yc is supercritical upstream. Okay, so then step 2, you must calculate H minimum. Okay, so H minimum by comparing height of weir H with the H minimum. So the condition of flow over weir can be established by if H is less than H minimum is in case 1. Okay, if H is equal to H minimum is in case 2. Okay, H more than H minimum, so in case 3. So then step 3 is you must find the y1, y2 and y3. So this is the step analyzing flow over broad crested weir. Okay, so in case 1, okay, if H is less than H1, so we get the subcritical upstream here, YC less than Y2 less by Y not here. So we get the, actually this is from, okay, actually from this is the big from the here. Okay, for the subcritical and supercritical here, I just put to here. Okay, based on the case here, case 1 here. Okay, based on case 1 here, we'll explain more about in this slide. Okay, so this is based on the case 1 here, subcritical upstream. Okay, when the supercritical upstream with the y naught less than yc. Okay, supercritical y naught is more than yc, so the y naught less than y2 less based on yc here. So the graph is based on this one. So the E minimum here, so we get the YC. Okay, E2 and E naught here. So we get the part here to get the E minimum and the H minimum and the H here. Okay, For the supercritical, subcritical here, so E minimum based on this, we get the YC. And E2, we get the Y2, and E0 here, so we get the Y1. So Y1 is equal to YC is equal to Y0. So we get this value. This is in case 1. Okay. So case 1, step by step, this is a calculation step by step here. Okay, calculate Y0 and YC. So you calculate Y0 and YC. If all sections, so you must use this Manning equation. Okay, this Manning equation for Y0 and YC. Okay, if the rectangular section, you must use this YC, and also the Y0 here. Okay, to all section, you must using the Manning here. Okay, and YC also for Y0 and YC rectangular section, you must do so. Okay, no need to worry, all this formula is given. Okay, not to worry. Okay, all this formula is given. Okay, just randomly put in list of formula so you can find from that formula. Okay, so calculate H, so using this all formula, okay, that I mentioned from the previous slide, and you use also the specific energy here. Okay, based on this one, and E minimum here. Okay, and for rectangular section based on this equation and using this equation. Okay, and we know that the H minimum is equal to E naught minus by E minimum. So you can get the H minimum. After you find the E minimum, okay, and you can get the H minimum based on the E naught. Okay, E naught actually is given. Okay, is given. You can calculate from based on E1 or E3 here. Okay, based on this concept here. Okay, so now to get the determinant of Y1, Y2, and Y3, so you must know that this equation. Okay, Y1 is equal to Y3 is equal to Y0. Okay, and E2 is equal to E0 minus by H. So you must remember this equation here. Okay, so use to determine the Y1, so you must use this equation based on the energy equation here. Okay, based on the energy equation, you just use the Y2 here. Okay, and also the same here based on rectangular section. Okay, now the case 2 here, okay, based on subcritical and supercritical is also the same here. Okay, actually this is just for the case 2. So the step by step is also the same as the case 1. Okay, the formula is also the same. Okay, but the E1 is equal to E3 is equal to E0 not. Okay, so this is based on case 2. Okay, you must remember this for case 2. So the formula is the same. Okay, the formula is same for calculate Y0 and YC and calculate the H minimum. Okay, but for the determine Y1, Y2, Y3, you must remember this basic formula. Okay, for this is for case 2. Okay, now with the case 3, H more than H minimum. Okay, based on this one, so the calculation here for case 3, so you must know this formula. Okay, based on the same formula for calculate Y0 and YC and calculate H minimum. Okay, but for the Y1, Y2, and Y3, you must know that the Y1 is not the same Y3 and not same Y0. Okay, so you get the minimum here, and you just using the same equation, but you have the prime here. Okay, so this is for case 3. Okay, so now we look at the calculation here. Okay, a 10 meter cube per second of flow is conveyed in a rectangular channel. So this is rectangular channel of 4 meter width. Okay, so given Q is 10, B is 4, N is 0.0015, S naught is 0.0075, and H is 0.92. Okay, so step 1, you must find determine Y0 and YC. Okay, using this equation based on rectangular channel. Okay, based in this formula. Okay, so use this formula, you just put the Y0 and the R here. Okay, R is equal to A over P. So you get this formula, and you just solve this calculation based on this try and error. Okay, so maybe you can use the try and error to get the Y0. Okay, so you get the Y0 based on try and error method. So you get the Y0 here. Okay, and use the YC here, you must use the rectangular section formula. So you get the 0.8605 meter. Say you get the YC here. Okay. And then, so we know that the Y naught is less than YC. So this is supercritical flow. Okay, so that's the step by step. Okay, now based on the step to calculate H minimum. Okay, so we use the specific energy equation formula here. So just put the value E naught here and the Q here until you get the value of E naught, the E at actually specific energy at normal depth. Okay, at normal depth, so you get the 1.369 meter. And we know that the E minimum is 3 over 2 times by the YC. Okay, YC you get 0.8605. So you get the value of E minimum is 1.291 meter. So we know that the H minimum is E naught minus by E minimum. So we get the value of H minimum is 0.078 meter. Now determines Y2. Okay, after you determine the Y2, so we get the H is 0.92 meter is more than H minimum. Okay, so this is in case 3. So is and get the hydraulic jump. So Y2 is equal to YC. So we get the 0.8905 meter. Okay, that's all. So to be continued in part B. Assalamualaikum warahmatullahi wabarakatuh.